Hi, everybody. Excuse me. Today's going to feel a little bit random. We have just some things that are connected and some things that are not connected to go over. We're going to start with talking about vectors and how they could also be complex numbers. Now, a complex number is a plus bi, or as you can see here, a minus bi. The a is the real part, so like a 7 or a 2. And then, of course, the part with the I is the imaginary part. So that could be anything. It could be I radical 3. It could be 1/2 I. Anything with an I is imaginary. So we got to graph this. Instead of calling this X and Y, they've got them called real and imaginary axes. And so you graph the real, obviously, in the real, and the imaginary on the imaginary part. So we're going to graph each of these vectors, and then we're also going to graph its conjugate. So if we take a look at this, 4 plus 3i. Now that would be on the real, we'd go right 4 and minus 3i, so we'd go down 3. So right 4 down 3, and so this is, I'm going to just call this vector A. Now the conjugate symbol is denoted with a little bar over just a lowercase letter. So a conjugate, if you recall, so the conjugate of A, and this is the symbol for conjugate, is 4 minus 3i. Oops, sorry, 4 plus 3i. So if we graph the conjugate, we're going to go right 4. That doesn't change, but now we're going to go up 3. And so this is the conjugate of A. For B, negative 2, so left 2 and up 4i, up 4. So it's just like regular graphing. So there is your vector B. And then the conjugate of B would be negative 2 minus 4i. So that's the conjugate of B. And for vector C, pure imaginary, you would not go left or right at all. You would just go straight up. So that's what a pure imaginary looks like. And then, of course, the conjugate for this is just negative 2i. You change the sign on the imaginary. So here the conjugate would just be straight down. So if you take a look at the pictures, if we take a look at, and I graphed all the originals with a black line and then all of the conjugates with a different colored line. And so you can see that each one is a reflection over the x-axis. So that's just what conjugates and vectors look like when you put them together. It's not anything super revolutionary or even something that's going to come up a lot, but sometimes it just helps to see the picture. The next part we're going to do on the calculator. If you're not sure how to put it into the calculator, there's a separate video from YouTube showing you how to put it in the calculator. Shows you the keys that you push, shows you problems you might run into, how to use the fraction key, how to switch it to complex numbers, how to put it into real versus complex, so A plus BI, where that mode is, all that good stuff. Now, if you do this without the calculator, it takes obviously a little bit longer, and you would be multiplying by these conjugates. Now, exception for the first one, in order to get rid of an imaginary, remember I squared is equal to negative 1. So if we square the I is actually gone. This is supposed to be an I. So you would multiply the top and the bottom here just by 3i. So the denominator would be multiplying and the top would be distributive property. When you write a complex number, it has to be A plus BI. Those are not my rules, those are just the rules. So if you don't put it in that order, it's actually incorrect. So if you were to say 7i plus 2, that is the wrong way to write it, and it is just wrong. So be careful with that. So if you put this in the calculator, switch it back to a fraction, or put it in with your fraction key, and you get 5 plus 2i over 3. Now the way the calculator writes it, and the video goes over this, but if you don't watch the video, it looks like 5 plus 2, like this, with the I out here. The I is really just with the 2. It's not with the whole thing, it's just with the 2. It's just the way the calculator is programmed. To get rid of this, you would multiply by the conjugate, 6 plus 8i, top and bottom. So it's a lot like radicals. Good news is you don't have to mess with any of that. We can just put this in the calculator and you get 9 plus 12i over 25. The calculator also will simplify this, which is nice. The conjugate on this number 4 would be negative 1 minus 2i. But again, don't mess with that. Put it in the calculator and you get negative 11 minus 2i. The entire thing goes over 5. Now the issue becomes when you have a problem like number 5. Number 5 will not go into the calculator because of the radical. So now we actually have to do it by hand. You knew there was going to be a trick. Here it is. So we're going to multiply the denominator by 5 minus I radical 3. And of course, whatever you do to the bottom, you have to do to the top. The whole problem is designed to get rid of the radical and the I all at the same time in the denominator. The denominator is the difference of two squares, so it's just first one squared minus second one squared. Now when you square this, I times I is I squared, and radical 3 times radical 3 is a plain 3. I squared is really negative 1, so that's going to come out, and in its spot's going to go a negative 1. So the denominator actually works out very, very well, and it ends up with 25 minus negative 3. So we end up with no imaginaries, no radicals in the bottom. It's the numerator that's a little bit trickier, and you will have to use FOIL or distributive property. So we'll get 15, then outside is a minus 3i radical 3. Inside these two, we get a minus 5i radical 2. And then when you multiply the last two together, they're both negative, so we get positive I squared. Radical 2 times radical 3 can be multiplied. So we're going to have to put some of this stuff together, but none of it matches. So that's a problem. Now the issue is it must have all real parts first. So 15 obviously is a real number. This is also a real number because this turns into negative 1. So then we get negative radical 6. Now the other two imaginary pieces, these two, doesn't matter the order, they just have to be next. Negative 3i radical 3 minus 5i radical 2. So it's messy, but it is not actually finished because 25 plus 3 is 28. So that's the numerator will be kind of messy like that, and the denominator should be just a plain number. Now adding and subtracting is really super easy. You can use the calculator on this, but it's almost easier not to, faster maybe. The calculator does like the parentheses, so you will have to put the parentheses around those numbers. But it's just like you would think it would be, combining like terms. Real plus real, so that's 3. And then imaginary plus imaginary, so we would get plus 3i. And that's it. With number 7, you have to change the signs. Negative 6 plus 7i. Distribute the negative, so then we'd have plus 2 minus 7i. And then, of course, here the i's add up to 0, which is allowed, and we just get negative 4. Now what they're going to do with this, complex numbers, we've already done this with vectors, which is why it's kind of inserted into this part. We're not going to call it distance and magnitude, magnitude and direction rather. We're going to call it absolute value and argument. So absolute value is the exact same thing as magnitude. Same formula, but we just use different terminology when we have a complex number. Argument is just the direction. That's all it is. We're going to use inverse tangent, and everything is going to feel very much the same. So A and B come from A plus BI instead of coming from component form. Same positions, first and second, A and B, alphabetical order. It's all right there. You can draw a picture if that helps you to figure out what quadrant you're in. And the picture ties back to what we started with that grid in the very front, the very first problem we did, which is why we did it. So we're going to graph 1 and then negative 3i, so that's going to be down here. And so I don't know if the triangle would help you, but this would be a 1, this would be a negative 3. We don't care about the hypotenuse. The absolute value of the number z, and it is a number, is just the square root of 1 squared. Now again, remember, 3i squared is 3 squared, and then I squared is negative 1. But we wanted to make sure you take the absolute value. Absolute value is in there, so we won't have any negatives. Even though I squared is negative 1, you won't get negatives because of the absolute value. So you've got to get rid of the absolute value. So we're going to have 1 plus 9. So this is just radical 10. You can leave it like that. And then for the argument, and you do write it ARG in parentheses Z. You put the name of the number in there, which I know is weird. But we're going to have inverse tangent of theta is equal to opposite -3 over, actually, I would not put the -3, 3 over 1. And then just figure it out, right? You're in the fourth quadrant, so you're going to get a positive angle. Take 360 minus that angle, and the angle is 288.43 degrees. Looks like number 9 here, this is missing an I. So I wanted to show you one that was maybe in a different quadrant. Second quadrant is difficult because a lot of times we don't get the second quadrant out of the calculator. So we're left 3 and up 7. So again, absolute value, ignore the negatives because you're taking the absolute value, 3 squared plus 7 squared. And this works out to be radical 58, which is simplified. The argument is the direction. So we have inverse tangent is equal to opposite over adjacent, and then adjust this. From the calculator, you get 66.8 degrees. Well, we don't want that. You got to do 180 minus that, based on the fact that it's in the second quadrant. So our angle here is 113.20 degrees. Now, graphing on the polar grid, I know a lot of you have done this in ALEKS. And if you haven't, you should, because it's really pretty easy. But I want to go through it and show you how this works. I don't know why these numbers are this way down here. This is like 60y. It's really 60 degrees. So that's not really a y. That's not. None of these are y's. These are degree symbols that somehow got converted to a y for whatever reason. Sorry about that. So I would always graph these backwards. A polar coordinate is in the form r theta. I would not graph it like that. You have to write it like that, but when you graph it, find the angle first. Now, these are labeled, as you can see on the polar grids. I won't promise that they'll always be labeled. They usually are, but you might run into some that aren't. And then you'll just have to figure out, well, how many sections do I have divided by, how many degrees if you're doing 90 or 180, and then figure out how many degrees are each section. Here you can see each angle is 15 degrees each section. So I'm just going to go through and do point A. So point A, 360 degrees. So I'd go to 60 degree line. So right here, go to the 60 degree line. The pole is the origin, and then that means you go out 3 rings on that 60 degree line. And that's where point A goes. Negative means if it's a negative r, negative radius, you shoot backwards through the pole. So you stay on the line. I'll do this one and draw on it. It's going to look a little bit strange. So we're going to go, here's your 30 degree line. Well, if it was 1.5, we would go towards the 30. We'd go this way. But we want to go backwards away from the 30, but stay on that same line. We want to go 1.5. So here's point B. For point C, again, another negative radius. So I would go to the 135 line. So 135, don't go towards the 135. Go away from the 135, back through the pole on that line, 2. So there's point C. Point D, 4, 0. Just like you think. 0 degrees, go out to the 4. 1, 2, 3, 4. This is point D. And then negative angles. We've been doing negative angles a long time. This isn't any different. Negative angles mean you spin down. So go to negative 240, which maybe is a little bit hard to remember because it's been a while since we've done that. Here, this is negative 180. Right, here's negative 240 is up here at 120. So this is where negative 240 is. So we come down and go all the way to negative 240. Now, it is a positive 5, so that means we're going to go towards that number 5 rings. And so here is point E. So watch the other video if you're not sure how to put it into the calculator, and then answer the questions on the Google form using your calculator, of course. And then the plotting the points are just multiple choice. It's pretty fast, and it's also obviously very easy because you just put the numbers in the calculator. The correct answers will come up on that Google form so you can check your answers.